Look up at the night sky on a clear evening, and you'll see a breathtaking tapestry of stars, constellations, and distant galaxies. But look a little closer, and you might notice something strange. There are places up there where the light seems to fade away, where the glittering crowds of stars thin out into profound, almost unsettling emptiness. These are the cosmic voids, immense regions of space that defy our expectations and challenge everything we think we know about the universe. They're not just gaps or blank spots. They're dynamic, evolving structures that make up the majority of the cosmos in terms of volume, yet they remain some of the least understood features of our reality. What if I told you that within these vast expanses of apparent nothingness lie secrets that could rewrite the story of the cosmos itself? It was the pioneering astronomer Vera Rubin who once said, "We have peered into a void and found that it peers back." That sense of mystery, that feeling that emptiness might actually be watching us, captures the eerie fascination these regions hold. Cosmic voids aren't just empty. They're actively shaping the universe around them. They influence how galaxies form and move, how dark energy accelerates the expansion of everything, and how matter itself is distributed across billions of light years. In many ways, these voids are the universe's quiet architects working behind the scenes, hidden in darkness, yet holding clues to some of the biggest questions we can ask. What is dark matter really? How did the universe evolve from a smooth, hot beginning to the structured cosmic web we see today? And what will ultimately become of everything we see and everything we don't? In this video, we're going to journey into those depths, into the heart of these intergalactic voids, to uncover what lies beneath the darkness. We'll explore how they formed, what strange properties they possess, and how cutting-edge research is beginning to reveal their hidden roles in the cosmic story. This isn't just a tour of empty space, it's an investigation into the nature of reality itself. You'll come away questioning what it truly means for something to be empty, and you might never look at the night sky the same way again. So join me as we venture into the great nothing and discover why sometimes nothing is everything. But what exactly are these cosmic voids, and why do they captivate astronomers so deeply? To call them simply empty would be a profound understatement. Imagine the grandest canyon you can possibly picture on Earth, and then multiply that scale by a factor of millions. These are regions of space so immense that light itself takes hundreds of millions of years to travel from one side to the other. Within these staggering volumes, the density of matter plummets to almost nothing. Where a typical galaxy cluster might be a bustling metropolis of thousands of galaxies, a void is more like a vast, nearly uninhabited desert, with perhaps only a few isolated galactic outposts scattered across its incredible expanse. The discovery of these voids completely upended our classical view of the cosmos. For a long time, the prevailing assumption was that on the largest scales, the universe was fairly uniform, a homogeneous soup of matter. But starting in the late 1970s and accelerating through the 80s and 90s, large-scale galaxy mapping projects began to reveal the truth. They showed us that the universe is actually structured like a colossal sponge or a cosmic web. Galaxies are not scattered randomly. They are concentrated into dense knots and long, winding filaments. And the voids are the great empty spaces in between those threads. This discovery was a monumental shift, forcing us to confront the powerful roles of dark energy and gravitational instabilities in sculpting the universe from its earliest moments. This is why physicist Laura Mersini-Houghton refers to voids as windows into the quantum origins of the cosmos. They are fossilized imprints of the most minuscule quantum fluctuations, that were stretched to astronomical sizes during the period of rapid inflation just after the Big Bang. Those tiny seeds of slightly lower density were the birthplaces of these voids. Over billions of years, as gravity pulled matter into the denser regions, these underdense areas expanded, becoming ever larger and emptier. So when we look at a void today, we are essentially looking back in time at the universe's most primordial imperfections. Their very existence is a critical test for our models of cosmology, telling us that our understanding of gravity, dark matter, and dark energy must account for these vast pockets of nothing. They are not passive absences but active players, their expansion influencing the motion of galaxies and the very rate at which the universe itself grows. So how does a universe that began in a hot, dense, and nearly smooth state end up with these immense, structured pockets of nothing? The story of void formation is written in the earliest moments of cosmic history, starting with the tiniest of imperfections. In the first fractions of a second after the Big Bang, the universe underwent a period of hyper-fast expansion known as inflation. During this time, the entire cosmos was a seething quantum foam, and within that foam, tiny fluctuations in energy and density were inevitable. These were not random. They followed the fundamental rules of quantum mechanics, meaning that on the very smallest scales, particles and energy would briefly pop into and out of existence, creating microscopic ripples. Inflation then took these quantum ripples and stretched them to absolutely enormous sizes, imprinting them across the entire observable universe. Think of it like blowing up a balloon with a faint, microscopic pattern on its surface. As the balloon inflates, that pattern becomes a large-scale structure you can clearly see. Those stretched-out ripples became the blueprint for everything we see today, the future sites of galaxy clusters, the filaments, and critically, the voids. The regions that started with just a tiny bit less density than their surroundings became the seeds for these great cosmic voids. After inflation ended, gravity began its slow, relentless work over billions of years. Matter, both the normal kind we see and the mysterious dark matter, was pulled by gravity toward the regions of slightly higher density. As this matter drained away into what would become the dense filaments and clusters of the cosmic web, the underdense regions were left behind. And because there was less matter there was less gravitational pull holding them together or slowing them down. This is the key. These underdense regions didn't just sit there passively. They began to expand faster than the universe around them. It's a gravitational paradox. Less gravity actually means more expansion. As the surrounding filaments grew denser and more massive, they effectively squeezed these voids, helping to define their boundaries and accelerate their growth into the vast, empty bubbles we detect now. We can watch this entire cosmic drama play out not with telescopes, but inside supercomputers. Sophisticated simulations like the Millennium Run and its successors take our best understanding of physics and run it forward in time, recreating the evolution of the universe from its smooth beginning to its complex present. These digital universes show us how small underdensities slowly expand, how neighboring voids sometimes merge into colossal supervoids, and how they are shaped and sculpted by the tightening grip of the dark matter filaments that surround them. They are dynamic, living structures. As the renowned astrophysicist Jeremiah Ostraker so eloquently put it, these voids are the negative image of the cosmic web, telling the story of what didn't happen. They are a record of the absence of collapse, a fossilized imprint of where matter decided not to go. And in the modern era, this process has gotten a powerful boost from a mysterious source, dark energy. As dark energy accelerates the overall expansion of the universe, its effect is most pronounced in the places where gravity's grip is weakest, inside the voids themselves. This makes cosmic voids some of the fastest-growing structures in the entire cosmos. They are being pushed apart from the inside, expanding even faster than the general Hubble flow. This ongoing acceleration ensures that voids will continue to grow larger and emptier, further defining the large-scale structure of the universe and ultimately determining its far future fate. The existence and behavior of voids are a beautiful demonstration of the cosmic tug of war between the inward pull of gravity and the outward push of dark energy, a fundamental battle that shapes the very architecture of reality. So if the cosmic web is a vast, interconnected network of galaxies and dark matter, then voids are the enormous empty rooms that give that web its shape and structure. But just as rooms come in all different sizes and shapes, from tiny closets to grand ballrooms, cosmic voids are not all the same. They vary tremendously, and by categorizing them, we can start to understand the different roles they play in the architecture of the universe. The main ways astronomers classify them are by their sheer size, their overall shape, and their internal density of matter. Let's start with the giants, the supervoids. These are the titans of emptiness, some stretching an almost incomprehensible 300 million light-years across. To put that in perspective, if you could travel at the speed of light, it would take you 300 million years just to go from one side to the other. Their scale is so immense that they don't just sit there passively, they actively interact with the fabric of the cosmos itself. Their vast underdensity creates a kind of gravitational hill. When the ancient light from the cosmic microwave background passes through a supervoid, it has to climb out of this shallower gravitational well, and in doing so, it loses a tiny amount of energy. This shows up in our telescopes as a subtle cold spot in the microwave sky, a direct and measurable imprint of nothingness on the oldest light we can see. On the opposite end of the spectrum are the mini-voids. Think of these as the bubbles within the larger bubbles. They are smaller underdense regions, often nested inside a much larger supervoid. Their presence tells us that even within these great expanses of nothing, there is still a finer level of structure. They are like the pockets of air within a slice of Swiss cheese, showing that emptiness itself has a complex texture when you look closely enough. Studying these mini-voids helps astronomers understand how larger voids formed and evolved, almost like studying the pebbles inside a cavern to understand how the cavern was carved out. Then we have the shapes. Some voids, through a combination of their initial conditions and the influence of their surroundings, have managed to form into remarkably spherical hollows. These near-perfect spheres are like cosmic bubbles, and their symmetry tells us that they formed in a relatively calm environment, free from major disruptive forces. They are the purest form of a void. In contrast, irregular voids are all angles and asymmetry, often stretched and sculpted by the powerful gravitational tides from a nearby galaxy cluster or a dense filament of the cosmic web. Their distorted forms are a record of their violent interactions with the crowded universe next door. Perhaps the most famous of all these voids is the Boötes void, often dubbed the Great Nothing. Discovered in the 1980s, it was a staggering revelation. Here was a region of space roughly 330 million light-years across that contained almost nothing. Early surveys found only a handful of galaxies in that immense volume, a number that has only slightly increased with more sensitive telescopes. It's so profoundly empty that if our Milky Way were at the center of the Boötes void, we would not have known other galaxies existed until the 1960s. It is the poster child for cosmic emptiness, but we don't have to look billions of light years away to find a void. We are living right on the edge of one. The local void is a massive, expanding region of space that borders our own local group of galaxies. Its gravitational influence is actually pushing our galaxy and others around us, contributing to our motion through the universe. It's a powerful reminder that these are not distant curiosities. They are part of our immediate cosmic environment, actively shaping the space we live in. By cataloging these different types from the spherical to the irregular, the mini to the super astronomers are doing more than just creating a taxonomy of emptiness. Each void type acts as a different kind of laboratory. Spherical voids are perfect for testing models of void formation, while irregular ones teach us about gravitational interactions. Supervoids allow us to probe dark energy, and mini-voids reveal the finer details of the cosmic web. This entire classification system is a crucial tool for mapping the universe's large-scale structure with ever greater accuracy, turning a simple observation of nothing into a precise science. And within that nothing, as we're about to see, lies the subtle but pervasive presence of the universe's most mysterious component. But if we could see the universe through the lens of gravity itself, a very different picture of these voids would emerge. While they appear overwhelmingly empty to our telescopes, they are not the perfect vacuums we might imagine. In fact, they are permeated by the universe's most dominant and mysterious component, dark matter. This invisible substance, which makes up roughly 27% of all mass and energy in the cosmos, doesn't just vanish inside these great voids. Instead, it forms a vast, faint, and incredibly diffuse web, a ghostly architecture that underpins even the emptiest regions of space. Supercomputer simulations of the cosmos show this with stunning clarity. We can watch as dark matter particles, governed only by gravity, stream in delicate currents. They flow slowly into the voids from the surrounding filaments, and then, pulled by the greater gravity of the dense walls, they flow back out again. This creates a subtle cosmic circulation system, a slow breath in the darkness, that plays a crucial role in how these voids evolve and expand over billions of years. This faint presence transforms our understanding of these regions. As researcher Elena Pierpaoli pointed out, voids become incredible natural laboratories. In the crowded, chaotic environments of galaxy clusters, the signal of dark matter is mixed and muddled with all sorts of other phenomena: violent collisions, intense magnetic fields, and superheated gas. But inside a void, the environment is far simpler. There's very little of that normal matter to complicate the picture. This simplicity allows scientists to isolate the pure gravitational effects of dark matter, to study its behavior in a near-pristine state. It's like trying to study the properties of water. Doing so in the middle of a stormy ocean with crashing waves and howling winds is incredibly difficult. But if you could study a single, calm drop of water in perfect isolation, you could learn so much more about its fundamental nature. That's what voids offer for dark matter research. This has profound practical implications for how we measure the universe. One of our most powerful tools for mapping the invisible mass of dark matter is a phenomenon called gravitational lensing. The gravity from any massive object, including the diffuse dark matter in a void, warps the fabric of space-time, bending the path of light from distant galaxies that passes through it. By carefully studying the subtle distortions in the shapes of millions of background galaxies, astronomers can create a map of the mass within a void, tracing out the delicate dark matter web that our telescopes cannot see directly. These measurements are vital for calibrating our models of cosmic expansion. The rate at which a void itself grows is directly tied to the amount and distribution of dark matter within it. By comparing the observed growth of voids to the predictions of our simulations, we can test and refine our entire understanding of the cosmos, putting fundamental physics to the test. So, the next time you hear about a cosmic void, remember that it is not truly a void in the sense of complete nothingness. It is a region dominated by a faint, web-like structure of dark matter, a hidden skeleton that gives these empty spaces their form and influences their destiny. This revelation completely shatters the classical idea of true emptiness. There is no such thing as a perfect vacuum on these cosmic scales. Even the deepest voids are inhabited by the ghostly presence of dark matter, which shapes the cosmos on the very largest scales. And while dark matter may be the dominant force in these regions, it is not entirely alone. This hidden architecture is accompanied by a tiny, trace amount of the ordinary atomic matter that makes up our world, a subject that leads us to our next fascinating layer of the void. Yet, even within these vast domains dominated by dark matter, a faint atomic presence persists. We now turn our attention to the ordinary stuff of the universe, the baryonic matter that makes up stars, planets, and us. It's a common misconception that these voids are completely barren. In reality, they contain a sparse but scientifically precious distribution of hydrogen gas and the occasional lonely star or galaxy. Detecting this ethereal matter is one of astronomy's greatest challenges, requiring the most powerful telescopes we have. Instruments like the Hubble Space Telescope peer into the depths of these emptiness, and after long, painstaking exposures, they reveal the faint, ghostly glow of dwarf galaxies and tenuous clouds of gas adrift in the immense darkness. These are not the bright, bustling galaxies of the cosmic web. They are more like isolated ships on a vast, dark ocean, barely visible on the horizon. What makes this scattered gas so incredibly valuable to scientists is its primordial nature. In the crowded environments of galaxy clusters, the gas between galaxies is anything but pristine. It's been repeatedly cycled through generations of stars, enriched with heavy elements forged in stellar furnaces, and then blasted out by supernova explosions. It's polluted, recycled, and constantly stirred, but the gas in the depths of a void has led a much quieter life. It has largely been left alone for billions of years, undisturbed by the violent dramas of star formation and galactic collisions. This means its composition is remarkably similar to the raw material that emerged from the Big Bang, overwhelmingly hydrogen and helium. As astronomer Renew Sen suggests, this makes voids incredible cosmic time capsules. They preserve a fossil record of the early universe, allowing us to directly sample the conditions that existed before the first stars ever switched on. By studying this gas, we can test our theories about the initial composition of the cosmos with a clarity that is simply impossible anywhere else. Occasionally, this primordial matter does manage to coalesce into full-fledged galaxies. These void galaxies are among the most intriguing and isolated objects in the universe. They are the true hermits of the cosmos, forming and evolving in near-total solitude, far from the gravitational influence of any major cluster. This profound isolation has a direct and dramatic impact on their life cycle. Without nearby galaxies to interact with, they experience very few galactic mergers or close encounters. This lack of interaction means they evolve at a much more sedate pace. Their star formation is not triggered or enhanced by external forces. It's a slow, steady process fueled by their own internal gas reservoirs. One of the most telling signatures of their isolation is their lower metallicity, a term astronomers use to describe the abundance of elements heavier than hydrogen and helium. With fewer past supernova to pollute their environment, the stars in these void galaxies are made from more primitive stuff, much like the very first stars to form in the universe. Studying these baryonic components, the pristine gas and the unique galaxies does more than just satisfy our curiosity about emptiness. It provides critical insights into fundamental cosmic processes. For instance, it helps us understand how galaxies accrete fresh gas to fuel new star formation over billions of years. In a void, this process happens in slow motion without interference, allowing us to see the basic mechanics at work. It also sheds light on the recycling of matter, showing us what happens when material is not constantly being reused and reprocessed in a crowded environment. The void, therefore, acts as a perfect control experiment, a natural laboratory where we can observe the simplest, most fundamental rules of galaxy evolution playing out in isolation. This clearer understanding of the rules in a quiet environment helps us untangle the far more complex physics of the bustling cities of the cosmic web. These isolated void galaxies are cosmic anomalies that defy the typical rules of galactic society. While most galaxies live in crowded clusters or along dense filaments, constantly interacting with their neighbors, void galaxies are the ultimate loners. They form and evolve in near-total solitude, adrift in an ocean of darkness that stretches for millions of light years in every direction. This profound isolation has a dramatic effect on their very nature. Without the gravitational tug of war and frequent collisions that are commonplace in busier parts of the universe, void galaxies are free to develop in their own unique, undisturbed way. They often appear smaller, with a distinct blue hue that signals a burst of youthful star formation, and their shapes are more likely to be irregular and asymmetric, lacking the classic spiral or elliptical forms we associate with galaxies that have been shaped by a lifetime of interactions. The work of astronomer Amy Barger has been pivotal in revealing the slow, gentle life cycle of these isolated systems. Her research shows that in the quiet depths of a void, galactic evolution operates on a completely different timetable. Without the triggering mechanisms of galactic mergers or the stripping away of gas by a dense intergalactic medium, star formation in these galaxies is a more gradual, self-regulated process. They aren't jump-started by external events. They simply consume their internal gas reservoirs at a leisurely pace. This results in galaxies that are, in many ways, living fossils. They preserve a record of what galaxy evolution looks like when it's driven purely by internal dynamics, offering a pristine control group that helps astronomers disentangle the complex effects of environment from the fundamental rules of galactic physics. Finding these faint, lonely giants is one of observational astronomy's great challenges. Their low surface brightness means they don't scream for attention in telescope surveys. Their light is spread thin and dim across their structure, making them incredibly difficult to distinguish from the background blackness of space. It requires incredibly deep, painstaking observations to tease out their subtle signatures. Yet the effort is profoundly worthwhile because their existence fundamentally challenges a long-held assumption. For decades, the prevailing wisdom was that rich, dense environments were necessary to nurture and shape galaxies. Voids were thought to be galactic deserts, incapable of supporting such complex structures. The discovery of void galaxies turned that idea on its head, proving that even the universe's emptiest regions can indeed give birth to and sustain stellar communities, albeit ones with a uniquely quiet and isolated character. Studying these outliers is crucial for completing our census of galactic diversity. They represent an extreme end of the environmental spectrum, and by understanding how they live and die in near-total isolation, we gain a more holistic view of all the possible pathways a galaxy can take. They force us to refine our theories of galaxy formation, ensuring they account for the full range of conditions the universe has to offer, from the crowded metropolitan centers of galaxy clusters to the solitary homesteads adrift in the great cosmic voids. This understanding of the unique matter within voids, from its primordial gas to its isolated galaxies, sets the stage for an even grander phenomenon, the way the voids themselves are moving and growing, expanding faster than anything else in the cosmos. This faster-than-average expansion isn't just a curious detail, it's a fundamental feature of their nature, driven by a simple but powerful principle of gravity. In the dense, crowded regions of the universe like galaxy clusters, gravity is king. It pulls matter inward, slowing down the expansion and eventually causing the cluster to collapse in on itself. But inside a void, the rules of the game are flipped. With so little matter, there's very little gravitational pull to counteract the natural expansion of space. It's like being in a boat that's barely anchored. When the tide comes in, you drift away much faster than the boats that are held fast by heavy anchors. In the cosmic context, that tide is the relentless push of dark energy, and it finds its most potent expression in these underdense regions. The void's expansion isn't just a gentle drift, it's an acceleration, a runaway effect where the emptiness literally begets more emptiness. This phenomenon, often called void acceleration, is a critical piece of the dark energy puzzle. As cosmologist Benjamin Wandelt so aptly describes them, voids are indeed cosmic accelerators, revealing the push of dark energy. They act as natural amplifiers for this mysterious force. While dark energy is causing the entire universe to expand at an accelerating rate, its effect is subtle and can be difficult to measure precisely across vast distances. But within a void, that subtle signal is turned up. The combination of weak internal gravity and the constant outward push of dark energy means that the space within a void stretches at a rate that can be up to 20% faster than the cosmic average, a finding confirmed by painstaking analysis of data from massive galaxy surveys like the Sloan Digital Sky Survey. This makes voids one of the most sensitive instruments we have for measuring the strength and nature of dark energy itself. This rapid growth has profound and observable consequences for everything around it. The void's expansion doesn't happen in isolation. It actively reshapes its cosmic neighborhood. Think of a void as a growing bubble in a pot of boiling water. As the bubble expands, it pushes the surrounding water outward. In the same way, an expanding void exerts a kind of pressure on the galaxies and matter at its edges. This creates a distinct pattern of motion that astronomers can actually detect. Galaxies located on the fringes of a void are observed to be streaming away from its center, caught in the outflow of this cosmic expansion. We can measure this motion through precise observations of redshift, the stretching of light waves as these galaxies move away from us. This isn't just the general expansion of the universe. It's a specific, localized river of motion directly caused by the void's growth. This dynamic behavior makes voids incredibly powerful laboratories for testing our most fundamental theories of the cosmos. The rate at which a void grows, the shape it maintains, and the way it influences surrounding matter are all predicted by our standard model of cosmology, which includes both dark matter and dark energy. If observations match the predictions, it strengthens our confidence in the model. But if they don't, it could be a sign that something is missing or that our understanding of gravity itself needs a revision. Some alternative theories of gravity, which seek to explain cosmic acceleration without invoking dark energy, make very specific predictions about how voids should behave. By meticulously mapping the growth and structure of thousands of voids, astronomers can put these theories to the test, using the emptiness of space to probe the deepest laws of physics. The dynamics of these great nothings are, therefore, essential for understanding the everything. This grand, interconnected architecture of the cosmos, this vast cosmic web, is fundamentally defined by the voids that shape it. Think of it not as a flat network of threads, but as a magnificent three-dimensional foam. The galaxies and the dark matter filaments are the soapy walls and struts of that foam, and the voids are the great empty bubbles inside. It's a structure of breathtaking scale and complexity, and what's truly staggering is that these voids aren't just minor features, they are the main event. They make up the overwhelming majority of the universe's volume, a full 80% of all space. So when we talk about the large-scale structure of everything, we are mostly talking about the architecture of nothing. The real action, the cosmic construction zones, are found at the boundaries where these two extremes meet, where the profound emptiness of a void presses up against the dense, matter-rich wall of a filament. These are the frontiers of the universe, sites of intense gravitational drama. Matter from within the void is slowly draining toward these boundaries, while the sheer expansion of the void itself is trying to push the filament apart. It's at this delicate interface that galaxies are often born and nurtured. The accumulating gas and dark matter at these edges provide the raw material for new galactic structures, making the rims of voids some of the most productive regions in the cosmos for star formation. It's a beautiful paradox. The emptiest places in the universe are directly responsible for creating some of its greatest concentrations of matter. This deep interconnectedness means that a change in one part of the web sends ripples throughout the entire system. A void that expands just a little faster than its neighbors, accelerated by a local dominance of dark energy, can exert a new gravitational influence on the filaments around it. This can alter the flow of matter into galaxy clusters, change the rate at which new stars are born, and even influence the ultimate fate of those structures billions of years from now. The entire cosmic web is a dynamic, breathing entity, and the voids are its expanding lungs. As physicist J. Richard Gott so perfectly described it, this structure is a sponge, and the voids are its holes. You cannot understand the sponge without understanding the holes that give it its form and function. Studying this intricate relationship is absolutely crucial for solving one of cosmology's biggest puzzles. How did a universe that began in a state of incredible smoothness and heat evolve into the complex, structured web we see today? The voids hold a key part of the answer. Their growth, their distribution, and their very shapes are a fossil record of that transition. By meticulously mapping where the voids are and how they are arranged, astronomers can work backwards to test theories about the initial conditions of the universe and the nature of the dark energy that continues to sculpt it. This grand pursuit, this mapping of emptiness, requires some of the most advanced observational tools ever created by humanity. Mapping the colossal emptiness of cosmic voids is one of modern astronomy's most ambitious and technically dazzling endeavors. It's a detective story played out across billions of light years, where the clues are not just the bright points of light we can see, but the profound absences in between. To even begin this mapping, astronomers don't rely on single, powerful telescopes pointed at one patch of sky. Instead, they undertake massive, systematic surveys that methodically scan huge portions of the cosmos, cataloging the precise positions and properties of millions upon millions of galaxies. Projects like the Sloan Digital Sky Survey, which began its work over 2 decades ago, have been fundamental. Using a dedicated telescope, it has created the most detailed 3-dimensional maps of the universe ever made, painstakingly recording the locations of galaxies and, by extension, charting the vast empty spaces that separate them. The more recent Dark Energy Survey has built upon this, using a supremely sensitive digital camera to peer deeper into the universe's past, all in the quest to understand how the cosmic web and the voids within it has evolved over time. The most crucial tool in this cosmic cartography is the measurement of redshift. When we look at a distant galaxy, the light it emits is stretched as it travels across the expanding universe, shifting its wavelength toward the red end of the spectrum. The greater this redshift, the farther away the galaxy is, and the longer its light has been traveling to reach us. By meticulously measuring the redshift of millions of galaxies, astronomers can calculate their distances from us with remarkable precision. This transforms a flat, two-dimensional image of the sky into a rich, three-dimensional model of the universe's structure. Within this vast digital cosmos, sophisticated algorithms then go to work. They aren't looking for clusters, they are hunting for emptiness. These programs identify the largest regions of space that contain significantly fewer galaxies than the cosmic average, effectively outlining the voids in 3 dimensions. It's like mapping an underground cave system by precisely noting where the solid rock isn't. But seeing where the galaxies aren't is only the first step. The real challenge is figuring out what is actually there, hidden in the darkness. This is where the phenomenon of gravitational lensing becomes an indispensable tool. As light from incredibly distant background galaxies travels through the universe on its way to our telescopes, it passes through these cosmic voids. While a void has very little mass, it isn't completely empty. That faint web of dark matter still exerts a tiny gravitational pull, which subtly warps the fabric of spacetime itself. This warping acts like a weak lens, bending the path of the background light and causing the shapes of those far-off galaxies to appear ever so slightly distorted. By analyzing the patterns of this distortion across thousands of galaxies, astronomers can perform a kind of cosmic tomography. They can create a mass map of the void, revealing the otherwise invisible skeleton of dark matter that gives the emptiness its structure and influences its growth. It's an incredible feat, using the distorted light from galaxies billions of light years away to weigh the nothingness in between. Other telescopes lend their unique sensors to this investigation. Giant radio telescope arrays, like the upcoming Square Kilometre Array, are tuned to detect the faint radio whispers of neutral hydrogen gas, the most abundant element in the universe. Even in the depths of a void, trace amounts of this primordial gas drift through the darkness. Detecting its faint signal allows scientists to measure its distribution and velocity, providing another independent way to probe the environment within these empty regions and understand the conditions that have persisted there for eons. Meanwhile, space-based observatories are taking the search to new heights. The European Space Agency's Euclid mission, for instance, is specifically designed to explore the dark universe. It will measure the shapes and redshifts of billions of galaxies with stunning accuracy, creating an ultra-high-resolution map of the cosmic web that will allow us to track the evolution of voids across cosmic time, watching how they grow and change from the ancient past to the present day. Of course, this entire process is filled with immense challenges. One of the trickiest is simply confirming that a perceived void is a true physical structure and not just an accidental gap in our data. Imagine looking at a forest from a distance. You might see a clearing, but you can't be sure if it's a real meadow or just a place where the trees are hidden behind a hill. In astronomy, this hill could be a foreground cloud of cosmic dust within our own galaxy that blocks our view, making a perfectly normal region of space appear empty. Astronomers must carefully account for these observational biases, using statistical models to distinguish genuine cosmic voids from mere illusions. Furthermore, the algorithms used to find voids can produce slightly different results depending on their specific parameters, meaning that defining the exact boundary of a void can sometimes be as much an art as it is a science. Despite these hurdles, the relentless pace of technological advancement is overcoming them. Each new survey is bigger, deeper, and more precise than the last. With every improvement in camera sensitivity, computational power, and analytical technique, we are peeling back the layers of these enigmatic spaces, transforming them from abstract curiosities into well-defined laboratories for testing our most fundamental ideas about the cosmos. To truly grasp the nature of these vast cosmic empties, we need more than just observations. We need a theoretical framework, a set of mathematical models that can explain not only what we see but also predict what we might find. The journey to model these voids begins with a surprisingly simple idea, treating them as perfect spheres. This spherical approximation is a powerful starting point, a way to capture the basic physics of an expanding underdense region without getting lost in overwhelming complexity. Imagine a perfectly round bubble growing in an infinite sea. This simple model allows theorists to derive fundamental equations about how a void's expansion rate depends on its density and the influence of dark energy. It's a crucial first step, a conceptual anchor that helps us understand the core principles at play before we add all the messy details of the real universe. But the cosmos is anything but a collection of perfect spheres. To move closer to reality, scientists employ more sophisticated statistical tools. This is where formalisms like the Press-Schechter theory and its extension, excursion set theory, come into play. Originally developed to predict the number of massive galaxy clusters in the universe, these statistical methods were cleverly adapted to describe the other end of the spectrum, the voids. The principle is based on those initial quantum fluctuations from the Big Bang. The theory tracks how a tiny region of space with a specific initial density will evolve over time. If the density falls below a critical threshold, that region is destined to become a void. These powerful statistical tools allow cosmologists to make broad predictions about the universe's void population, how many voids of a certain size we should expect to find, essentially creating a cosmic census for emptiness before we even look through a telescope. It's a probabilistic prediction of nothingness. However, to witness the full, dynamic life story of a void, from its birth in the primordial fireball to its current status as a vast, growing emptiness, we must turn to the most powerful tool in the modern cosmologist's kit, the supercomputer simulation. Projects like the Illustris TNG and Eagle simulations are nothing short of digital universes. They start with the best estimates of the initial conditions of the cosmos and then code in all the known laws of physics, gravity, hydrodynamics, the formation of stars and black holes, and the feedback of energy they produce. Then they set the simulation running and watch billions of years unfold in a matter of months. Within these virtual cosmos, we can watch voids form, grow, and interact in exquisite detail. We see how small voids often merge together to form colossal supervoids, like soap bubbles combining in a sink. We observe how the surrounding filaments of dark matter squeeze and sculpt them into irregular shapes. These simulations are our time machines, allowing us to test our theories against a complete, visual record of cosmic evolution. Yet, even in a simulated universe, the story isn't always straightforward. The void in cloud scenario is a fascinating example of the complex dynamics these models reveal. It describes the fate of a small void that has the cosmic misfortune of forming inside a much larger, overdense region that is destined to collapse into a massive cluster, a cloud. While the small void initially begins to expand, it is eventually overwhelmed by the relentless gravitational collapse of the enormous structure surrounding it. The larger cloud collapses faster than the small void can expand, ultimately crushing it out of existence. This scenario reminds us that voids are not immortal. They can be born and they can die, their fate inextricably linked to the larger cosmic environment in a constant tug of war between expansion and collapse. It is this ability to test physics in extreme conditions that makes voids so invaluable. As cosmologist Alice Pisoni puts it, they test our models at the extremes of density. This has made them a key battleground in one of the most profound debates in modern physics, whether our theory of gravity is complete. Our standard model of cosmology, known as lambda cold dark matter or lambdactum, relies on Einstein's theory of general relativity to work on cosmic scales. But some scientists propose that what we call dark energy might actually be a sign that our understanding of gravity is wrong at very large distances. These are known as modified gravity theories, with FR gravity being a prominent example. These theories propose subtle changes to Einstein's equations that become significant in regions of extremely low density, precisely the conditions inside a cosmic void. If general relativity is correct, voids should expand at a specific rate. But if a modified gravity theory like FR is correct, the expansion would be different. By using incredibly precise measurements of void sizes, shapes, and growth rates from new telescopes, astronomers can place tight constraints on these alternative theories, effectively using nothingness to test our understanding of one of the universe's fundamental forces. Every new model, whether it confirms our standard picture or challenges it, serves a vital purpose. They are the essential bridge between raw, observational data and deep physical understanding. They help us interpret the faint signals we detect from the edges of emptiness and allow us to make predictions about what future, more powerful telescopes might discover. And with each improvement in our theoretical tools, we don't just get answers, we uncover deeper, more nuanced questions about the limits of our understanding and the true nature of the dark, expanding cosmos we call home. But the story of these voids reaches back even further, to the very dawn of time itself, and it's written in the oldest light we can see. This is the cosmic microwave background, the faint afterglow of the Big Bang that fills every corner of the universe. For decades, this radiation was seen as a nearly perfect snapshot of infant cosmos, a uniform blanket of light. But as our maps of the CMB became exquisitely detailed, thanks to satellites like Planck, astronomers began to notice something strange. Scattered across this ancient canvas were subtle anomalies, mysterious cold spots where the temperature of the radiation dipped just a tiny fraction below the average. And the most intriguing part, the locations of some of these coldest spots seemed to align with the positions of the largest supervoids we had mapped in the modern universe. This was not a coincidence. It was a direct conversation between the universe's first light and its largest structures, a conversation mediated by one of cosmology's most subtle effects. This phenomenon is known as the integrated Sachs-Wolfe effect, and it's a concept that ties together gravity, light, and the expansion of the universe in a beautifully intricate way. To understand it, picture a CMB photon, a particle of light that has been traveling for over 13 billion years to reach our telescopes. Its journey is an epic saga across an ever-changing cosmos. As it flies through space, it must navigate the shifting landscape of gravitational potentials, the hills and valleys, in the fabric of space-time created by the distribution of matter. Now, if the universe were not expanding, or if it were expanding in a simpler way, the energy a photon gained falling into a gravitational valley would be perfectly cancelled out by the energy it lost climbing out the other side. Its total energy would remain unchanged, but we live in a universe dominated by dark energy, a universe where the expansion is accelerating. This acceleration causes the gravitational hills and valleys to actually evolve and become shallower over time. So, when a photon enters a vast, growing void, a massive, expanding gravitational valley, it loses a significant amount of energy falling in. But by the time it climbs out the other side, the valley itself has become shallower due to the void's accelerated expansion. The climb out therefore requires less energy than the fall in. the photon emerges with a net loss of energy. Since a photon's energy directly correlates with its temperature, this net energy loss translates into a cooling effect. That CMB photon arrives at our detector very slightly colder than its neighbors that traveled through denser regions. This is the integrated Sachs-Wolfe effect in action, the imprint of evolving cosmic structures on the primordial light. It's a tiny signal, incredibly difficult to detect against the background noise of the universe, but the statistical power of mapping thousands of voids against the full Skyplank data has revealed a measurable correlation. As researcher Istvan Shapuri so eloquently noted, these voids are indeed leaving their fingerprints on the oldest light in the universe. They are reaching across billions of years to subtly alter the signature of creation itself. This discovery is far more than just a fascinating curiosity. It's a powerful new tool for probing the nature of dark energy. The strength of the ISW effect, the amount of cooling it induces, depends critically on the properties of dark energy, specifically its equation of state, a parameter that describes the relationship between its pressure and density. By meticulously measuring the temperature decrements associated with vast cosmic voids and comparing them to the predictions of different cosmological models, scientists can place tight constraints on what dark energy actually is. A stronger than expected cold spot could hint at a form of dark energy with unusual properties, potentially pointing toward physics beyond our standard model. Furthermore, this effect provides a crucial test for the cosmological principle, the foundational idea that the universe is homogeneous and isotropic on the largest scales. The fact that the CMB anomalies align with the largest structures we see today suggests a deep connection between the very large and the very old, reinforcing that the universe is indeed a coherent, interconnected whole. Yet, as with any profound discovery, this one is not without its controversies. Some analyses debate the statistical significance of the correlation, questioning whether the observed cold spots are truly caused by the ISW effect from voids, or if they could be the result of other, more mundane factors or even just chance alignments in the data. These debates are the essential engine of scientific progress, driving more precise observations and more sophisticated analyses. Missions like the upcoming Euclid Space Telescope are designed to map both the cosmic web and its voids with unprecedented precision, while future CMB experiments will measure the faint temperature variations with even greater sensitivity. Together, they will settle these debates and sharpen this incredible tool, allowing us to read the story of dark energy written in the cold, ancient light that has passed through the deepest voids in creation. This remarkable ability to leave a chill on the ancient light of the cosmic microwave background is just one way voids reveal the secrets of dark energy. But their role as a probe for this mysterious force goes far deeper, turning these expanses of nothing into some of the most powerful natural laboratories we have for understanding why the universe is flying apart faster and faster. The reason is beautifully simple. Dark energy's repulsive effect is most obvious where gravity's attractive pull is at its weakest. In the crowded, dense environments of galaxy clusters, the powerful gravity of all that matter is fighting a fierce tug of war against the background push of dark energy. But inside a vast cosmic void, there is almost nothing to push back. It's the difference between trying to measure a gentle breeze in the middle of a hurricane versus feeling it out in the open calm of a vast, empty plain. In the void, the signal is clean, clear, and amplified. This is precisely why cosmologist David Weinberg describes voids as ideal probes, noting they amplify the effects of dark energy. To harness this power, astronomers are undertaking monumental projects to essentially make cosmic time-lapse films of these empty regions. By using massive surveys like the Dark Energy Survey, and the upcoming Legacy Survey of Space and Time, scientists will map the three-dimensional positions and sizes of thousands upon thousands of voids at different distances. Because looking deeper into space is like looking back in time, this allows them to track how a void grows and evolves over billions of years. The rate of this growth is exquisitely sensitive to the strength and nature of dark energy. It's a direct measurement of the push that's stretching these empty bubbles from within. By comparing this observed growth to the predictions of different theoretical models, astronomers can tightly constrain dark energy's so-called equation of state, a fundamental parameter that tells us whether this force is constant or changing over time, which is crucial for predicting the ultimate fate of everything. But measuring size is only one way to use these cosmic tools. Their shapes also tell a profound story. As light from distant galaxies travels through the universe on its way to our telescopes, it must pass through these voids. The subtle gravitational field of the void's dark matter skeleton acts as a weak lens, warping the fabric of space-time and very slightly distorting the shapes of those background galaxies. By meticulously measuring this subtle distortion, a technique called weak gravitational lensing, astronomers can create a mass map of the void. The way a void's shape distorts under this effect reveals the precise interplay between the matter trying to hold it together and the dark energy trying to push it apart, offering an independent measure of dark energy's influence. Another ingenious technique uses the ghosts of sound waves from the early universe as a cosmic ruler. In the first few 100,000 years after the Big Bang, the universe was a seething plasma where matter and light were locked together. Pressure waves called Baryonic acoustic oscillations rippled through this hot soup. These waves froze in place when the universe cooled enough for atoms to form, leaving a permanent, faint imprint on the distribution of matter. This imprint manifests as a preferred distance between galaxies. That distance becomes a standard ruler, a known measurement stick that astronomers can use to gauge the scale of the cosmos at different epochs. When they look at the distribution of the few galaxies inside a void, they can look for this preferred scale. By seeing how this ruler appears to be stretched or squeezed when viewed through the expanding void, they can measure the geometry of the universe and the rate of its expansion with incredible precision, all thanks to the pristine, simple environment that the void provides. What makes this void-centric approach so powerful is that it provides a completely independent and complementary path to understanding dark energy, one that cross-checks the results from other methods like observing distant supernova or counting galaxy clusters. Each technique has its own potential pitfalls and systematic errors, but by comparing answers from all of them, astronomers can triangulate on the truth, reducing the chance of being led astray by a hidden bias in any single method. The humble void, once seen as a mere curiosity, is now at the forefront of observational cosmology, offering a clear, amplified view of the force that dominates our universe and whose nature remains one of the greatest mysteries in all of physics. This brings us to one of the most profound applications of these cosmic laboratories, the ability to test the very laws of gravity themselves. For centuries, our understanding of gravity has been built upon the firm foundation of Newtonian physics and later Einstein's theory of general relativity, which describes gravity not as a force but as a curvature of space-time by mass and energy. These theories have been spectacularly successful, predicting everything from the orbit of Mercury to the existence of black holes. But the discovery of dark energy and the accelerating expansion of the universe has prompted a bold question. Could our theory of gravity be incomplete on the very largest scales? Could what we call dark energy actually be a sign that gravity itself behaves differently in environments of extreme low density? Cosmic voids, with their vast, underdense volumes, are the perfect place to go looking for an answer. This is where alternative theories of gravity, like modified Newtonian dynamics or MUND, and its more sophisticated relativistic cousin, FR gravity, enter the picture. These theories propose subtle tweaks to Einstein's equations, changes that are designed to explain the observed acceleration of the universe without the need for a mysterious dark energy component. The key prediction of these modified gravity models is that their effects would be most pronounced in regions where the gravitational field is exceptionally weak, precisely the conditions found in the heart of a cosmic void. In the standard model, a void expands faster because of dark energy's push against minimal gravitational resistance. But in a modified gravity scenario, the expansion rate itself might be different because the fundamental law of attraction operates in a new way in such an empty space. It's a subtle distinction with monumental implications. The way to test this is to make exquisitely precise observations of how matter behaves in and around these voids. According to general relativity, the motion of a galaxy on the edge of a void should follow a very specific path as it is influenced by the gravitational pull of the surrounding filaments and the push from the void's expansion. If an alternative theory of gravity is correct, those motions might show a tiny but detectable anomaly, a slight deviation from the predicted path that can't be explained by the visible matter alone. It's like watching a single car on a vast, empty highway. If the laws of physics were slightly different, you might notice its speed or direction change in a way that defies standard expectations. By carefully tracking the velocities of thousands of galaxies around thousands of voids, astronomers are essentially setting up a massive, natural experiment to see if gravity plays by the same rules everywhere. This is the grand ambition behind missions like the European Space Agency's Euclid telescope. Euclid is not just another observatory. It is a precision instrument designed to create the most detailed map of the cosmic web ever made, charting the shapes and redshifts of billions of galaxies across 10 billion years of cosmic history. With this unprecedented dataset, scientists will be able to measure the growth and shapes of voids with phenomenal accuracy. They will be able to see if the observed distortion of void shapes from gravitational lensing, or the peculiar motions of galaxies around them, match the predictions of Einstein's general relativity, or if they begin to reveal the fingerprints of a new law of physics. As physicist Claire Burridge so evocatively stated, these voids are where gravity might finally show its true colors, revealing its fundamental nature in an environment unlike any other. The potential implications of such a discovery are staggering. If a deviation from general relativity were confirmed within these vast emptinesses, it would trigger nothing less than a revolution in our understanding of fundamental physics. It would mean rewriting the textbooks and rethinking our most basic concepts of space, time, and energy. It would open a door to a new world of physics beyond our current standard model. However, it is crucial to note that to date, the weight of evidence still strongly supports our standard cosmological model, known as lambda cold dark matter, or lambdactum, which incorporates both dark matter and dark energy within the framework of general relativity. The observed properties of voids, their abundance, their growth rates, their lensing effects have so far mostly aligned with what this standard model predicts. This doesn't make voids any less valuable, quite the opposite. In science, a stringent test that a theory passes is just as important as one it fails. Each void that behaves exactly as general relativity predicts helps to strengthen the theory's standing and tightens the constraints on any potential alternatives, telling us exactly how any modified theory must behave to fit the data. This rigorous testing deepens our knowledge far beyond just abstract theory. By using voids to probe the limits of our gravitational models, we gain a much sharper understanding of the cosmic acceleration that is shaping the fate of the entire universe. Whether that acceleration is driven by a new component of the universe like dark energy or by a modification to gravity itself, the study of voids is providing the crucial data we need to tell the difference. This pursuit beautifully illustrates the scientific method at its best, using the most extreme environments nature provides to stress test our ideas, pushing them to their limits in our endless quest to understand the fundamental rules that govern everything we see. These vast cosmic voids are not static, frozen relics of the early universe. They are dynamic, living entities with their own life cycles, growing and changing over billions of years in a process that is fundamental to the evolution of the entire cosmos. If we could rewind the tape of the universe back to its early chapters, we would find a very different landscape. The voids of the infant cosmos were not the immense, near-empty bubbles we see today. Instead, they were far smaller, more numerous, and surprisingly much denser. In the first few billion years after the Big Bang, the overall density of matter was higher everywhere, and the gravitational tug of war between regions was far more balanced. An underdense region back then might have been only slightly emptier than its surroundings, a small pocket of slightly lower density nestled within a universe that was, on the whole, much more crowded and compact. As the eons passed, the relentless forces of gravity and expansion began to sculpt this primordial roughness into the grand structures we recognize. Gravity acted as the great organizer, relentlessly pulling matter out of the underdense regions and into the waiting arms of the nascent filaments and clusters of the cosmic web. This draining effect had a profound consequence for the voids. With less and less matter inside them, their internal gravitational pull weakened even further, allowing them to expand faster than the universe around them. It's a classic case of the rich getting richer and the poor getting poorer, but in a cosmic sense. The dense regions became denser, and the empty regions became emptier, accelerating their own growth in a powerful feedback loop. This process was supercharged by the rising influence of dark energy, which began to dominate the universe's expansion around 5 billion years ago. Dark energy's repulsive force finds its purest expression in these underdense regions, pushing them apart from the inside and causing them to balloon in size at an ever-increasing rate. This grand evolution is not a solitary process, it's a social one. Voids interact with each other and their environment in a complex cosmic dance. Neighboring voids often merge, much like soap bubbles coalescing into larger ones. A smaller void, expanding at the edge of a much larger one, can eventually be absorbed, its identity lost as it contributes to the growth of a colossal supervoid. This process is what astronomers refer to as void hierarchy, a fascinating structuring of emptiness itself. At the same time, these expanding voids are constantly being squeezed and shaped by the very structures they help to define the dense, surrounding filaments of the cosmic web. The result is a universe in a state of constant flux, with voids growing, merging, and being sculpted, all while pushing the galaxies at their boundaries further away. This beautiful, dynamic interplay led the esteemed astronomer Simon White to describe it as a cosmic ecology, a system where voids act as the expanding bubbles in a great universal foam, their growth and interactions defining the large-scale architecture of everything. The implications of this evolution ripple across the cosmos, directly impacting the story of galaxy formation and the distribution of dark matter. As a void grows, it clears out its interior, but it also pushes matter ahead of it, effectively piling up material at its edges. This creates dense shells of matter around the void, which become prime locations for the birth of new galaxies. The evolution of a void, therefore, doesn't just create emptiness, it actively seeds creation at its boundaries. Furthermore, the dark matter web within a void stretches and thins as it expands, altering the gravitational landscape and influencing how matter flows into and out of these regions over time. To truly witness this billion-year saga, astronomers turn their telescopes to the distant, ancient universe. By looking at high redshifts, we are essentially looking back in time, observing voids when they were young. Comparing these ancient voids to their modern counterparts allows us to trace their developmental timeline, to watch a small underdensity transform into a vast emptiness. This observational timeline is then compared to the predictions of our most sophisticated supercomputer simulations. When the real universe and the digital universe agree, it gives us tremendous confidence in our models of cosmology. When they disagree, it points the way toward new physics, new understandings of dark energy, or a new appreciation for the complex processes that have shaped the cosmos from nothing into everything we see today. While the theoretical frameworks and grand simulations help us understand voids in general, some of these cosmic emptinesses have earned individual fame, becoming celestial landmarks that astronomers return to again and again. The most renowned of them all is undoubtedly the Boötes void, a name that evokes a profound sense of mystery and scale. Discovered in 1981 by astronomers Robert Kirshner and his team, this region of space presented a staggering puzzle. Stretching an almost incomprehensible 330 million light-years across, it was so devoid of galaxies that it quickly earned the nickname the Great Nothing. To put that scale into a human perspective, if our Milky Way were placed at its center, the night sky would be almost completely black, devoid of neighboring galaxies. We would not have even known other galaxies existed until the mid-1960s, when telescopes finally became powerful enough to peer beyond our local stars. Early surveys found only a handful of galaxies in that immense volume, a number that has only modestly grown to around 60 with more sensitive modern instruments. This is a density so low it defies imagination. Imagine a single grain of sand in a vast, empty concert hall, and you begin to grasp the profound isolation within the Boötes void. But the Boötes void is far from the only notable emptiness charted on our cosmic maps. Much closer to home, the Taurus void exerts a subtle but measurable influence on the motion of our own galactic neighborhood. This expansive region of underdensity contributes to the peculiar velocities of galaxies in our local sheet, including our Milky Way, acting as a gravitational void that subtly pulls and pushes on the matter around it. Then there is the Sculptor void, an irregularly shaped expanse that serves as a fascinating counterpoint to the more spherical voids. Its distorted form is a clear record of its dynamic history, likely shaped and sculpted by powerful gravitational interactions with the dense filaments and clusters that surround it, proving that even nothingness can bear the scars of cosmic conflict. And we cannot overlook the sheer immensity of the giant void in Canes Venatici, one of the largest known structures of its kind. Its scale is so grand that it doesn't just sit passively. It actively influences the cosmology of its entire region, affecting how galaxies are distributed and how light travels through that part of the universe. A critical insight that emerged from studying these famous voids is that they are never completely empty. The term void is a relative one, describing a region of drastically lower density, not absolute nothingness. The Boötes void, for all its fame as the Great Nothing, still contains those roughly 60 galaxies. While that number is vanishingly small for such a volume, their very existence is scientifically precious. These isolated island universes are like rare diamonds scattered across a vast, dark plain, and each one is a unique laboratory for studying galaxy evolution in the most extreme environment imaginable. Their presence forced astronomers to refine their theories, moving from the idea of true emptiness to a more nuanced understanding of underdensity. This realization also highlighted the technological limits of our galaxy surveys. The first maps of the Boötes void were made with the instruments available in the 1980s, and they simply weren't sensitive enough to detect the faintest, most diffuse galaxies that might have been lurking in the darkness. Each improvement in telescope technology has revealed a few more of these hidden residents, teaching us that our perception of nothing is always limited by the power of our eyes. This ongoing process of discovery shows us that for every famous colossal void like Boötes, there are undoubtedly countless smaller, less famous voids that are equally important to the cosmic story. The grand supervoids capture our imagination, but the hierarchy of emptiness includes a full spectrum of sizes. These smaller voids, often nested within larger ones or tucked away in the complex knots of the cosmic web, can act as fine-tuning tools for our models. They might hold clues to specific aspects of gravitational theory or dark matter behavior that are harder to detect in their giant cousins. As we continue to catalog these structures, from the most famous to the utterly anonymous, we build a more complete picture of the universe's large-scale architecture. And within the most isolated depths of these voids, we find the most extreme galactic inhabitants, whose strange and quiet lives demand a closer examination all their own. Drifting in the profound isolation of a cosmic void, a galaxy known as MCG plus 010201 holds a title that captures its existential reality more than any catalog number ever could. Astronomers call it the loneliest galaxy. Imagine a single spiral island of stars, separated from its nearest galactic neighbor by over 1 million light-years of near-total emptiness. This isn't just a poetic notion. This extreme isolation fundamentally rewires a galaxy's very nature, creating celestial objects that are unlike any found in the crowded urban centers of the universe. In the bustling galactic clusters, galaxies are constantly jostled, merged, and stripped of their gas by gravitational interactions. But out here, in the quiet darkness of the void, evolution proceeds at a glacial pace, governed by a completely different set of rules. This solitude leaves a clear chemical signature. Void galaxies like our lonely friend are often characterized by remarkably low metallicity. In astronomy, metals refer to any element heavier than hydrogen and helium. The carbon in our cells, the oxygen we breathe, the iron in our blood. These elements are forged in the nuclear furnaces of stars and are scattered into space by violent supernova explosions, enriching the surrounding gas from which the next generation of stars will form. In a dense cluster, this process happens again and again, rapidly polluting the galactic environment with these heavier elements. But in a void, the story is different. With very few neighboring galaxies and a much lower rate of star formation and stellar death, this cycle of enrichment is drastically slowed. The gas within and around a void galaxy remains primordial, much like the raw material that existed after the Big Bang. Consequently, the stars that form from this gas are made of more primitive stuff, offering astronomers a rare window into the chemical conditions of the early universe. This pristine gas reservoir is another defining feature. Isolated from the gravitational tug of war that can strip galaxies of their fuel in clusters, void galaxies often hold onto massive stores of neutral hydrogen gas. This abundant fuel supply allows them to sustain star formation over much longer timescales. While a cluster galaxy might experience a brief, intense burst of star formation triggered by a collision before having its gas ripped away, a void galaxy can engage in a slow, steady, and prolonged period of creating new stars. This isn't a dramatic firework display. It's the gentle, sustained glow of embers, allowing these galaxies to avoid the boom and bust cycle that dictates life elsewhere. This often results in populations of stars that are, on average, younger and bluer than their cluster counterparts, giving many void galaxies a distinct azure hue. Their physical forms tell a story of a quiet life, but not always a perfectly orderly one. Without the frequent interactions that mold most galaxies into neat elliptical or grand spiral structures, void galaxies can develop anomalous and irregular morphologies. Some exhibit disturbed disks, their shapes slightly warped not by a recent collision, but perhaps by the gentle, persistent accretion of gas from the void. Others might display rare structures like polar rings, a band of stars, gas, and dust orbiting perpendicular to the main disk of the galaxy. These peculiar features are often the ghosts of interactions so rare and ancient that they stand as frozen monuments within the void, their stories preserved due to the lack of subsequent events to erase them. This is why astronomer Lynn Matthews refers to these objects as living fossils of galaxy evolution. They are not primitive themselves, but their slow, undisturbed development allows us to observe processes that are often obscured or overwritten in more active environments. They are the control group in the grand experiment of galactic astronomy, showing us what happens when a galaxy is left to evolve in peace, governed primarily by its own internal dynamics. By studying them, we can isolate the effects of environment, answering fundamental questions about gas accretion, the efficiency of star formation, and the impact of internal feedback from supernova without the complicating noise of external gravitational influences. Comparing a void galaxy to a cluster galaxy is like comparing a solitary homesteader living off the land to a city dweller navigating a dense metropolis. The homesteader is self-reliant, develops unique skills, and changes slowly according to the seasons. The city dweller is constantly adapting to crowds, traffic, and the immediate influence of countless neighbors. One is not better than the other, but they represent two extreme outcomes shaped entirely by their surroundings. This stark contrast teaches us that a galaxy's destiny is not written solely in its initial mass or composition, but is profoundly dictated by its cosmic zip code. The empty spaces of the void don't just contain galaxies, they actively create a unique class of them, and in doing so, they exert an influence that ripples far beyond their own seemingly insignificant borders. To truly appreciate the grand architecture of the cosmos, we must shift our perspective from the individual components to the overall design. The universe isn't a random scattering of galaxies. It's a highly organized, three-dimensional web, a cosmic tapestry of unimaginable scale. And the threads of this tapestry are only defined by the empty spaces between them. Voids are not passive bystanders in this structure. They are its active sculptors. Their immense, expanding volumes act like cosmic cookie cutters, pressing against the surrounding matter and forcing it into the dense walls and filaments that form the recognizable web. This process is fundamental. As a void grows, its gravitational influence, or more accurately, its lack of gravitational pull, creates a kind of pressure that herds galaxies and dark matter ahead of it, effectively corralling them into the dense structures that outline its borders. It's a gravitational feedback loop on a billion-year timescale, where the growth of emptiness directly dictates the formation of cosmic richness. This dynamic interplay gives rise to a phenomenon known as void-driven structure formation. Imagine a growing bubble in a pot of boiling water. As the bubble expands, it pushes the surrounding water outward, creating a dense, circulating ring around its edge. In the cosmos, the expanding void acts as that bubble, and the surrounding matter is the water. This pushing effect amplifies the natural density contrasts in the universe. Regions that were already slightly denser become even more so as matter is squeezed into them by the encroaching emptiness. This makes the edges of voids, the frontiers between nothing and everything, the most fertile grounds for galaxy formation in the entire universe. It's here, in these dense shells swept up by the void's expansion, that gas clouds collapse, dark matter halos merge, and new galaxies are born at a prolific rate. The void, therefore, doesn't just create emptiness, it actively seeds creation at its boundaries, proving that something can indeed come from nothing. This establishes a profound co-evolution between the voids and the clusters. They are two sides of the same cosmic coin, locked in a gravitational dance that has been ongoing since the universe was young. The clusters and filaments grow denser and more massive through mergers and accretion, and in doing so, they exert a greater gravitational pull on the voids they surround, helping to define their shapes and sometimes even squeezing them into irregular forms. Simultaneously, the voids expand faster, pushing back against these dense structures and driving more matter into them. It's a continuous feedback loop, a self-perpetuating cycle where each structure shapes and is shaped by the other. This is why the words of cosmologist Sergei Shandarin ring so true. Voids are indeed the architects of the cosmic web. They provide the negative space that gives the entire structure its form and definition. When we step back and look at the universe on its very largest scales, this architectural design reveals a startling pattern. The arrangement of voids isn't random. It follows a roughly cellular or foam-like structure. Picture the foam on a freshly poured latte. The bubbles are of various sizes, they merge and connect, and the walls between them form an interconnected network. This is precisely how matter is organized in the cosmos. Voids of all sizes, from smaller mini-voids to colossal supervoids, fill the volume of the universe, and the galaxies are predominantly confined to the intricate, interconnected walls that separate them. This foamy pattern is a direct prediction of our standard model of cosmology and is one of the strongest confirmations that our understanding of the universe's evolution from a smooth beginning to a clumpy present is correct. To move from this beautiful analogy to hard science, cosmologists use powerful statistical tools to quantify this structure. One key measure is the void probability function. This isn't just a simple count of empty regions. It's a sophisticated statistical tool that calculates the probability of finding a region of a given size that contains absolutely no galaxies. By comparing the observed distribution of voids, their sizes, shapes, and how they are clustered, to the predictions of this function, scientists can perform a rigorous test of the cosmological principle. This principle states that on sufficiently large scales, the universe should look the same in all directions and from every location. The fact that the observed foam-like structure of voids aligns so well with these statistical predictions is a powerful confirmation that our universe is indeed homogeneous and isotropic when we zoom out far enough. It tells us that the same physical processes have been at work everywhere, creating a coherent and predictable large-scale architecture. Understanding this intimate relationship between voids and the cosmic web does more than just explain the past, it allows us to forecast the future. The rate at which voids grow is exquisitely sensitive to the content of the universe, particularly the amount and nature of dark energy. By meticulously measuring their expansion and how it changes over time, we can refine our models of cosmic evolution. This helps us predict how the distribution of matter will change billions of years from now. Will the voids continue to merge into one giant, ever-expanding emptiness as dark energy dominates, or could some other fate await the cosmic web? The answers are written in the growth of these nothingnesses, and by learning to read their expansion, we are essentially learning to read the destiny of the entire cosmos. The expansion we see within these cosmic voids isn't just a fascinating detail of their behavior. It's a powerful lens through which we can peer into the ultimate destiny of everything that exists. The fate of our entire universe may very well be written in the growth of these great nothings. In our current understanding, where dark energy dominates and its repulsive force continues to accelerate the expansion of space, the future for these voids is one of unchecked growth. They will continue to balloon in size, becoming ever larger and ever emptier as the eons stretch on. The galaxies that currently dot their boundaries will be pushed further and further apart, their collective light fading as the distances between them become so vast that not even light can bridge the gaps. This leads us toward a potential finale known as the heat death of the universe, a state not of fire and fury but of cold, silent stillness. In this distant future, the universe would reach a state of maximum entropy, where matter and energy are so perfectly diffuse and evenly distributed that no new stars can form, no new structures can coalesce, and the cosmos effectively runs out of the usable energy required for any further change or activity. It would be the final, eternal equilibrium, a cosmic sunset that never gives way to a new dawn. Some theoretical models paint an even more dramatic and violent end, one where the relentless push of dark energy doesn't just lead to a quiet fade, but to a catastrophic tearing apart of the very fabric of reality itself. This is the scenario known as the Big Rip. In this hypothesis, dark energy doesn't just accelerate, it grows stronger over time. If its repulsive force were to become infinite, it would eventually overcome all other forces in the universe. First, it would shred the cosmic web, pulling galaxy clusters apart. Then, it would tear individual galaxies to pieces. As the end draws near, the overwhelming force would rip apart stars and planets. In the final moments, even atoms, molecules, and the very fabric of spacetime would be torn asunder. The growth rates of cosmic voids are a critical testing ground for this terrifying idea. If observations show that voids are expanding at an accelerating rate that aligns with the most extreme models of dark energy, it could lend credence to the possibility of a big rip. Their behavior acts as a cosmic barometer, measuring the pressure that might one day blow the entire universe apart. But regardless of a quiet heat death or a violent rip, the overarching narrative is one of increasing isolation, and voids are the primary agents of this cosmic solitude. As they expand, neighboring voids will inevitably begin to interact and merge. Imagine two growing soap bubbles pressing against each other. Their shared wall will thin and eventually rupture, allowing them to coalesce into a single, larger bubble. On a cosmic scale, this process will repeat over and over across billions of years. The smaller voids of today will merge into the supervoids of tomorrow, and those supervoids will themselves eventually merge. Some cosmologists speculate that in the far, far future, this could lead to a universe dominated by one unimaginably giant void, a near-total emptiness where any remaining islands of matter are so isolated from one another that they are utterly and forever alone, unaware that anything else exists in the cosmos. This is the profound idea that physicist Brian Greene alludes to when he suggests that voids may be the harbingers of the universe's final state. They are not just structures, they are the embodiment of the universe's tendency toward dispersion and isolation. While these visions of the end of time are deeply speculative, they are not mere science fiction. They are hypotheses grounded in our best physical models, and they highlight why the meticulous study of voids is so critically important. By measuring the precise growth rates of voids today, by charting how their expansion has changed over cosmic history, and by comparing these observations to the predictions of different dark energy models, astronomers are gathering the empirical data needed to test these ultimate scenarios. The voids provide a real-world, observational anchor for our theories about the end of everything. They transform a philosophical question about fate into a measurable problem in physics. The data we collect now from these expanding emptinesses are the clues that will help us refine our predictions, moving us closer to understanding whether the cosmos is destined for a long, quiet sigh or a final, explosive shout. This grand perspective forces us to confront not only the physical fate of the universe, but also the profound philosophical weight of emptiness itself. Yet this scientific revolution in our understanding of nothingness finds a powerful echo in the creative expressions of humanity. Voids have long served as a profound metaphor in art and literature, symbolizing everything from paralyzing isolation and existential dread to boundless potential and the blank slate of creation. The iconic Infinity Rooms by artist Yayoi Kusama use mirrors and light to create illusions of endless, empty space, immersing the viewer in a void that is both awe-inspiring and deeply personal, reflecting the infinite within the confined. In literature, from the existential bleakness of Samuel Beckett's barren landscapes to the vast, mysterious emptiness of space in science fiction, the void acts as a character in itself, a force that challenges the protagonists, strips away pretense, and reveals fundamental truth about the human condition. These artistic interpretations are not mere flights of fancy. They are a different language for processing the same profound reality that cosmologists study. They explore the emotional and psychological weight of nothingness, giving form to the awe and trepidation we feel when confronted with the scale of our own insignificance within the cosmic arena. This duality shows that the void is not just an astronomical phenomenon but a fundamental human concept, constantly challenging us to find meaning in the absence of it. Ultimately, the greatest philosophical gift of these cosmic voids is their power to force a reconciliation between science and philosophy, between empirical measurement and existential wonder. They dissolve the artificial barrier between these two ways of knowing, proving that a question about the large-scale structure of the universe is inevitably a question about the very nature of reality itself. Astronomer Carlos Frank's observation that voids remind us that the universe is mostly nothing, yet that nothing has structure, is more than a beautiful paradox. It is a guiding principle for a new kind of cosmic humility. They teach us that emptiness is not a void in understanding but an invitation to it. This rich interplay, where a quantum fluctuation and a poet's metaphor can be two different approaches to the same profound mystery, endlessly deepens our appreciation of the cosmos. It transforms our journey from one of simply mapping emptiness to one of understanding our place within it, setting the stage for the incredible technological tools that allow us to undertake this quest. The quest to understand these vast cosmic voids is being propelled by a technological renaissance, a new golden age of astronomical tools that are fundamentally changing the game. We are no longer limited to simply inferring the existence of these empty regions. We are now beginning to probe their inner workings with a clarity that was pure fantasy just a generation ago. At the forefront of this revolution are the space-based observatories that rise above the blurring effects of Earth's atmosphere. The James Webb Space Telescope, with its colossal gold-plated mirror and exquisite infrared sensitivity, acts as an ultimate time machine. It is uniquely equipped to stare back into the early universe and study high redshift voids, those infant emptinesses that existed when the cosmos was only a few billion years old. By examining the faint, ancient galaxies that managed to form within these primordial voids, Webb can tell us about the conditions within them, measuring their gas content and the growth rates of their resident galaxies, providing a direct window into how these structures have evolved over the vast majority of cosmic history. Meanwhile, here on the ground, an entirely different kind of instrument is tuning into the universe's most abundant element. Massive radio telescope arrays, most notably the upcoming square-kilometer array, represent a monumental leap in our ability to hear the cosmos. The SKA will not be a single dish but a vast network of thousands of antennas spread across 2 continents, working in concert to create a collecting area of unprecedented scale. Its primary mission in void research is to map the distribution of neutral hydrogen gas, the primordial fuel for star formation. Even in the deepest voids, trace amounts of this gas drift through the darkness, emitting a faint radio whisper at a specific wavelength. The SKA's incredible sensitivity will allow it to detect this whisper, charting the invisible rivers and pools of hydrogen within these empty regions. This will reveal how gas flows into and out of voids, how it accretes onto isolated void galaxies, and whether the physical properties of this gas differ from that found in denser environments, offering a completely new perspective on the ecosystem of emptiness. This flood of new observational data would be meaningless without the computational power to make sense of it all. The other pillar of this revolution is happening not at remote mountaintop observatories, but in the humming server rooms of supercomputing centers around the world. The simulations of the past were impressive, but they were often forced to make simplifications, treating dark matter as the only important player or modeling galaxies as simple points of light. Today's most advanced cosmological simulations, with names like Illustris TNG and Eagle, are achieving a breathtaking new level of realism. They now incorporate the complex physics of baryonic matter, the ordinary atoms that make up stars, gas, and black holes. This means they can simulate the feedback from supernova explosions that heat gas and push it out of galaxies, and the intense radiation from quasars that can shut down star formation. By running these incredibly detailed simulations and then comparing the virtual voids they produce to the real ones observed by telescopes like Webb and the SKA, scientists can perform a rigorous test of our entire standard model of cosmology. It's a constant cycle of prediction, observation, and refinement that is sharpening our understanding to a fine point. This cycle is fueled by a fire hose of data from massive, dedicated sky surveys. The Dark Energy Spectroscopic Instrument, mounted on a telescope in Arizona, is not taking pretty pictures. It is methodically measuring the precise redshifts of tens of millions of galaxies, building a staggeringly detailed 3-dimensional map of the universe that will allow us to identify and measure voids with statistical power we've never had before. Following close on its heels, the Vera-C, Rubin Observatory's legacy survey of space and time will take this to another level entirely, imaging the entire visible sky every few nights for a decade. This will not only provide a static map but a movie of the cosmos, allowing astronomers to track subtle changes over time and detect incredibly faint objects within voids that were previously invisible. The sheer volume of data from these projects is itself a challenge, driving the development of new machine learning algorithms that can automatically find and classify voids, measure their properties, and search for correlations that might escape the human eye. The ultimate goal of all this technological investment is to reduce the nagging uncertainties that have long plagued cosmology. Every observation has a margin of error, and every model has simplifying assumptions. By combining data from multiple, independent sources, the infrared light seen by Webb, the hydrogen maps from the SKA, the galaxy positions from DESI, and the weak lensing signals from Rubin astronomers can cross-check their results. This multi-messenger approach to void studies helps to cancel out the systematic errors inherent in any single method, leading to far more robust and reliable conclusions about the true nature of dark energy, the properties of dark matter, and the validity of gravity itself on the largest scales. We are moving from an era of informed speculation into an era of precision measurement, where the mysteries of the cosmos are not just seen but are truly quantified, setting the stage for the next great leap in our understanding, which will inevitably lead us to confront the profound questions that still remain unanswered. Even as our maps of these cosmic voids grow more detailed and our simulations more sophisticated, we are continually reminded that for every answer we uncover, a dozen new and even more profound questions emerge from the darkness. The very nature of scientific exploration ensures that the frontier of knowledge is always moving, and when it comes to these vast expanses of nothing, that frontier is perhaps wider and deeper than anywhere else in cosmology. We have built an impressive framework of understanding, but it is a framework punctuated by glaring gaps and tantalizing mysteries that push the very limits of our physics. One of the most pressing and fundamental questions revolves around the precise mechanics of dark energy within these regions. We know that voids expand faster than the rest of the universe, and we know dark energy is the engine behind that acceleration. But the exact nature of that relationship remains infuriatingly vague. Is dark energy's influence uniform within a void, or does it vary, perhaps stronger, at the very center of the emptiness? Could the accelerated expansion of a void actually be generating more dark energy in a feedback loop we don't yet understand? Pinpointing the exact role of this mysterious force is more than academic. It is the key to predicting whether the universe will end in a frozen whisper or a catastrophic rip. Current and future surveys are designed to measure the growth rates of voids across cosmic time with ever greater precision, hoping to catch dark energy in the act and reveal its true character. Looking back even further to the very first instance of existence, another tantalizing possibility arises. Our standard model suggests that the voids we see today grew from tiny quantum fluctuations during the inflationary period. But could there be a class of primordial voids that were born even earlier, or that formed through a completely different mechanism? Some speculative theories suggest that the violent processes in the first fraction of a second of the Big Bang might have created exotic structures, defects in space-time, or bubbles of different physical laws that could have left behind vast primordial emptinesses as their signature. Finding evidence for such ancient voids would be like discovering a fossil from a time before time as we know it, forcing a radical rewrite of our cosmic origin story and potentially offering a glimpse into the physics that operated at energy scales we can never hope to recreate on Earth. Closer to home, in a temporal sense, the very existence of void galaxies presents a beautiful puzzle that challenges our models of galactic genesis. How do you build a galaxy in the profound quiet of a void, without the external triggers of galactic collisions or the tidal forces from nearby giants that are thought to spark star formation in cluster environments? It's like trying to understand how a single, isolated tree grew in the middle of a vast desert without any apparent source of water or fertile soil. The slow, internal processes must be radically different, perhaps relying on a gentle, continuous trickle of pristine gas from the void itself, a mode of growth that has been all but erased in the crowded environments we typically study. Understanding this quiet genesis is crucial because it might represent the universe's default, most peaceful method of building galaxies, a process that is simply drowned out by the noise everywhere else. Then there are the mysteries that seem to connect the largest scales to the smallest, weaving a thread through the entire history of the cosmos. The apparent statistical alignment between the positions of the largest supervoids and the coldest spots in the cosmic microwave background is a persistent anomaly that both tantalizes and frustrates cosmologists. While the integrated Sachs-Wolfe effect provides a plausible explanation, some analyses suggest the correlation might be stronger than the theory predicts. This has led to more exotic proposals. Could these alignments be a sign of something stranger, like a pre-Big Bang structure imprinted on our universe, or a curvature in the very fabric of space-time that we have not yet accounted for? Resolving this mystery will require exquisitely precise maps of both the modern cosmic web and the ancient light of the CMB, a task that will push our observational capabilities to their absolute limits. This scientific speculation naturally bleeds into the realm of science fiction and philosophical wonder. The possibility of void civilizations is a staple of cosmic horror and adventure tales, playing on the chilling idea of intelligent life that evolved in perfect isolation over billions of years, so alien that their very existence is unimaginable to us. While this remains firmly in the domain of fiction, it underscores a real scientific truth. The environments within voids are so different that any life there would have a completely different view of the cosmos. Their night sky would be almost perfectly black, their sense of cosmic loneliness absolute. They might deduce the existence of other galaxies only through the most sophisticated science, making their entire philosophical and scientific worldview fundamentally different from our own. This leads us to perhaps the most mind-bending question of all, one posed by theorists like Laura Mersini-Houghton. Could these voids contain clues not just to our universe but to a multiverse? Some cutting-edge theories suggest that the vast, accelerating expansion of a void could be the incubator for a new universe, budding off from our own in a process of eternal inflation. In this scenario, what we perceive as a cosmic void might actually be a cosmic womb, a region where the laws of physics are so stretched and diluted that a new Big Bang becomes possible, giving birth to an entirely separate universe with its own physical constants. If there is any evidence to be found for this staggering idea, it would likely be hidden in the subtle patterns of the CMB or the peculiar expansion dynamics of the largest voids, a faint signature of our universe touching another. This pursuit, which blends cosmology with fundamental particle physics, exemplifies the new interdisciplinary approach required to solve these puzzles, combining deep space observation with the mathematics of quantum gravity. The enigma of voids, therefore, is far from a niche curiosity. It is a central driving force of scientific curiosity, a constant reminder that the universe's emptiest places hold the most profound secrets, compelling us to look deeper and think bigger about the nature of reality itself. To truly grasp the majesty of the cosmic web, we must move beyond simply cataloging its parts and begin to understand how they relate to one another. Think of the universe not as a random scattering of glitter, but as a meticulously organized city, where each district has its own unique character, rules, and purpose. On one end of this cosmic metropolis, we have the dense, bustling downtown cores, the galaxy clusters. These are the gravitational powerhouses of the universe, immense cities of thousands of galaxies, all bound together by their mutual gravity, buzzing with energetic activity, violent collisions, and searing hot gas. They are places of extreme density and powerful gravitational pull, where the pace of life is frantic and the environment is anything but tranquil. In stark contrast, the cosmic voids are the great, expansive national parks surrounding the city. They are not just quieter or less crowded, they operate under an entirely different set of physical laws. Where a cluster's gravity pulls everything inward, a void's inherent underdensity allows it to expand outward, pushed by the mysterious force of dark energy. The gravitational potential within a void is far weaker, creating a shallower well in the fabric of spacetime. This fundamental difference in density and dynamics dictates everything that happens within these regions, from the slow, isolated evolution of their few resident galaxies to the rate at which the space itself stretches. It's the difference between the intense, crowded pressure of a city center and the open, accelerating expansion of a wilderness preserve. Connecting these urban centers and natural preserves are the cosmic filaments, the magnificent highways and bridges of the universe. These long, winding tendrils of dark matter and galaxies act as the primary transportation network, ferrying matter from the underdense voids toward the hungry clusters. They often form the intricate boundaries around voids, acting as the walls that contain and define these expanding bubbles. And where these filaments intersect, they can create vast two-dimensional structures known as walls or sheets, like the Sloan Great Wall, one of the largest known structures in the universe. These sheets are like the sprawling suburban neighborhoods that eventually give way to the dense urban clusters at their intersections. This comparative framework is not just for classification, it's a powerful diagnostic tool. By studying the sharp boundaries where a void meets a filament, astronomers can witness cosmic structure formation in action. These frontiers are sites of intense gravitational shearing, where matter from the void is being accreted onto the denser web, often forming sheet-like structures that highlight the beautiful diversity of cosmic architecture. Understanding how these different structures interact, how a growing void pushes against a filament, or how a cluster gravity pulls matter from a nearby wall, allows scientists to build more accurate models of the cosmic ecosystem. It reveals the universe not as a collection of isolated objects, but as a single, dynamic, and interconnected whole, where a change in one district sends ripples through all the others. This holistic view, built on understanding these stark contrasts, fundamentally enriches our picture of how the universe is organized, from its densest hubs to its most empty expanses. For centuries, the prevailing wisdom in astronomy was rooted in what we call the cosmological principle, the idea that on the largest scales, the universe is homogeneous and isotropic, meaning it should look roughly the same in every direction. This assumption of a fairly uniform distribution of matter was a comfortable foundation for our models, but in the late 1970s, that foundation began to crack, thanks to a new generation of ambitious galaxy surveys. Astronomers were no longer just looking at the sky, they were beginning to map it in a systematic way, and the picture that emerged was anything but uniform. Instead of a smooth soup of galaxies, they found hints of a lumpy, structured cosmos, with hints of immense, empty regions that defied all expectations. The true breakthrough came with the work of astronomers Stephen Gregory and Laird Thompson. In 1978, they published a landmark paper analyzing the distribution of galaxies in the constellation Boötes. Their analysis revealed something staggering, a vast spherical region where the number of galaxies plummeted to almost nothing. They had accidentally discovered the first confirmed cosmic void. This wasn't a small gap, it was a chasm of emptiness on an unprecedented scale. The Boötes void, as it became known, was a profound anomaly. If the universe was truly uniform, such a gigantic desert of space simply shouldn't exist. Its discovery was a direct challenge to the cosmological orthodoxy, forcing astronomers to confront the possibility that the universe's large-scale structure was far more complex and textured than anyone had dared to imagine. It was the moment the concept of a cosmic void moved from theoretical possibility to observable reality. This initial discovery needed confirmation, and it came from a monumental project that would forever change our view of the cosmos. The Center for Astrophysics Redshift Survey, or CFA survey, led by the pioneering astronomers Mark Davis, John Huckra, Dave Latham, and John Tonry throughout the 1980s. This project was revolutionary because it didn't just catalog where galaxies were on a flat, two-dimensional map of the sky. It added the crucial third dimension of depth by measuring their redshifts. This allowed the team to calculate distances and plot the positions of thousands of galaxies in three-dimensional space for the very first time. When they did, the results were breathtaking. The galaxies weren't scattered randomly like sprinkles on a cupcake. They were arranged in a vast, intricate network of dense filaments and sprawling, empty bubbles. The CFA survey didn't just confirm the existence of the Boötes void. It revealed that voids were everywhere, fundamental and ubiquitous features of the cosmic architecture. This was the birth of the cosmic web paradigm, a new way of seeing the universe that we now take for granted. The journey of understanding didn't stop with mere discovery. Each technological leap brought a new level of refinement to our view of these nothingnesses. In the early days, a void was simply defined as a place with very few galaxies. But as surveys grew larger and more precise, from the 2-degree field galaxy redshift survey to the monumental Sloan Digital Sky survey, our definition evolved. We began to understand that voids had complex shapes, sizes, and internal structures. We learned that they weren't completely empty, but contained a faint trace of galaxies, gas, and dark matter. Theoretical models and sophisticated computer simulations helped us understand their life cycle, from their birth in the quantum fluctuations of the Big Bang to their accelerated growth driven by dark energy. Our understanding shifted from seeing voids as simple, static absences to recognizing them as dynamic, evolving entities that actively shape the universe around them. This historical arc is a powerful testament to the scientific method itself. It's a story of how new evidence, gathered through technological innovation, can overturn long-held assumptions and force a paradigm shift. The discovery of voids shows that observation must always lead theory. We have to look at the universe with clear eyes and be willing to let it tell us its story, even when that story contradicts our most cherished beliefs. The map of the cosmic web, with its magnificent voids, is now a cornerstone of modern cosmology, a permanent reminder that the universe is far stranger and more wonderful than we ever thought possible. And this scientific revelation invites us to consider a much older, more human relationship with the idea of nothingness. Long before telescopes could map the vast emptiness between galaxies, humanity was already grappling with the concept of the void, weaving it into the very fabric of our origin stories and artistic expressions. This deep-seated fascination with nothingness reveals a profound truth about us. We are compelled to give shape to the shapeless and find meaning in the meaningless. In the ancient Greek tradition, the starting point of everything was chaos, not chaos in the modern sense of disorder, but a vast, yawning gap, a primordial void that existed before the gods, the earth, or the heavens. It was the first thing to come into existence, a neutral and empty space from which the first deities like Gaia, Earth, and Eros, love, could emerge. This wasn't a nothingness of absence, but a nothingness of potential, a blank canvas awaiting the first brushstroke of creation. This theme of a creative void is echoed powerfully in Hindu cosmology with the concept of sunyata, often translated as void or emptiness. But in this philosophical tradition, it carries a much deeper meaning than simple nothingness. It represents the underlying ground of all reality, the state of pure potentiality from which all forms manifest and to which they all eventually return. It is the ultimate reality behind the illusion of the material world, a concept that challenges the very notion of separate existence. Similarly, in the ancient Egyptian creation myth, the universe began with none, a dark, limitless, and unknowable ocean of chaos, a watery void that contained within it the unformed seeds of all life. waiting for the moment of differentiation. Across these cultures, the void wasn't a terrifying end point. It was the necessary beginning, the silent, dark womb that made all of existence possible. It was the ultimate source. This mythological heritage flows directly into the art and philosophy of the modern world, where the void continues to be a powerful source of inspiration and terror. The iconic Japanese artist Yayoi Kusama has spent a lifetime exploring this theme through her mesmerizing infinity mirror rooms. These installations use mirrors and light to create the illusion of an endless, boundless space, dissolving the boundaries of the self and immersing the viewer in a sublime and sometimes overwhelming experience of infinite void. It's a deeply personal yet universal exploration of self-obliteration and cosmic wonder, using the tools of art to evoke the same feelings astronomers describe when peering into the Boötes void. In literature, the void takes on a more existential dimension. From the barren, empty landscapes in Samuel Beckett's plays that mirror the internal emptiness of his characters, to the terrifying, cold vacuum of space in science fiction classics like Arthur C. Clarke's 2001 A Space Odyssey or the recent film Ad Astra, the void becomes a character in itself. It is the ultimate antagonist, representing the utter indifference of the universe, the profound isolation of consciousness, and the stark reality of our own mortality. It's the great, silent backdrop against which all human drama plays out, reducing our struggles to a fleeting whisper in an infinite silence. What this rich cultural tapestry shows us is that the scientific and the humanistic explorations of the void are not separate paths. They are two different languages describing the same profound mystery. The astronomer who maps the distribution of dark matter in a supervoid and the philosopher who meditates on Sunyata are, in a sense, engaged in the same project, trying to comprehend the nature of nothingness and its relationship to everything that is. Scientific discoveries about cosmic voids don't diminish these cultural interpretations. They enrich them, providing a real, measurable foundation for our metaphors. When we learn that voids make up most of the universe's volume, it adds a staggering, empirical weight to the ancient intuition that creation emerged from a vast emptiness. Our art, our stories, and our myths were ahead of our science, intuitively grasping a deep truth about the cosmos that we are only now beginning to quantify with telescopes and satellites. This cultural lens doesn't distract from the science. It adds a crucial layer of depth, meaning, and emotional resonance to our exploration, reminding us that we are not just observers of the cosmos, but a part of it, trying to understand our place within its immense and mostly empty expanse. This beautiful interplay between abstract wonder and practical discovery leads us to a surprisingly grounded question. While contemplating the void might expand our minds, does it have any tangible use here on Earth? It turns out that the pursuit of understanding nothingness yields incredibly practical rewards, pushing the boundaries of technology and methodology in ways that benefit us all. It might seem like studying vast expanses of nothingness is the most abstract scientific pursuit imaginable, a purely intellectual exercise with no connection to our daily lives. But the truth is, the relentless drive to map and understand cosmic voids has produced a cascade of practical innovations that reach far beyond astronomy, pushing the boundaries of technology in ways that benefit us all right here on Earth. The challenges of finding emptiness in a universe of data are so immense that they force us to invent entirely new ways of seeing, and those new tools often find powerful applications in completely unexpected places. This is a beautiful example of how exploring the most fundamental questions about the cosmos so often leads to serendipitous advancements that touch our everyday world. Consider the monumental task of void mapping. Modern sky surveys like the Sloan Digital Sky Survey or the Dark Energy Survey don't just give us a pretty picture. They produce petabytes of data, a dizzying flood of information on the positions, colors, and shapes of billions of galaxies. Finding the voids in this data isn't like looking for a hole in a piece of Swiss cheese. It's an incredibly complex computational problem of identifying the largest possible regions with the statistically lowest density of points in a three-dimensional point cloud that spans billions of light years. To solve this, cosmologists have had to pioneer sophisticated algorithms and data analysis techniques. These aren't just simple scripts. They are advanced machine learning routines that can identify patterns, classify structures, and handle datasets of a scale that was unimaginable just a few decades ago. And it turns out, the algorithms developed to find nothing in the cosmos are perfectly suited for finding something incredibly valuable here on Earth. These same data sifting techniques are now being adapted to map the complex networks of the human brain, to track the spread of information or disease through global social networks, and to optimize massive logistics and supply chain systems for global corporations. The tools built to understand the large-scale structure of the universe are proving equally powerful for understanding the large-scale structure of our own world. The research also delves into the physics of the extremely sparse matter that does reside within these voids. While we call them empty, they are not perfect vacuums. They contain a very diffuse, low-density plasma of ionized gas. Studying how this primordial matter behaves, how it interacts with radiation, and how it remains stable in such a radically isolated environment provides crucial insights into the fundamental behavior of plasmas. This is not just academic. It has direct implications for one of the most promising future energy sources on Earth, nuclear fusion. Here, the challenge is to contain and stabilize an incredibly hot, high-energy plasma within a magnetic field to achieve a sustained fusion reaction. The physics of stabilizing a low-density plasma in the vastness of a void can offer valuable counterpoints and insights for physicists trying to control a high-density plasma in a fusion reactor like a tokamak. Furthermore, understanding how materials and states of matter behave in such extreme isolation can inform new frontiers in materials science, potentially leading to the development of novel substances or coatings with unique properties. The pursuit of accuracy in cosmology has also driven the development of some of the world's most powerful supercomputers and most sophisticated simulation software. Creating a virtual universe from the Big Bang to the present day, one that accurately models the formation and evolution of voids, requires an astonishing amount of computational power and incredibly complex code that can handle the laws of gravity, hydrodynamics, and particle physics simultaneously. The software frameworks and immense processing power developed for these cosmological simulations are now invaluable tools for other fields. Climate scientists use adapted versions of this code to run incredibly detailed models of Earth's climate system. Aerospace engineers use the computational methods to simulate airflow over new wing designs or the stresses on spacecraft during launch. The quest to simulate the cosmos has, in effect, helped us build better tools to simulate and understand our own planet and our own technology. Perhaps one of the most tangible applications is in the direct design of future space missions. The European Space Agency's Euclid telescope and NASA's upcoming Nancy Grace Roman Space Telescope were specifically designed with void cosmology in mind. Their instruments are optimized to measure the subtle distortions of galaxy shapes caused by the dark matter in voids, and to map the three-dimensional positions of millions of galaxies to find these empty regions. The technology developed for these missions, the exquisite charge-coupled devices, the ultra-stable guidance systems, The complex data processing pipelines represents the bleeding edge of optical and digital engineering. This technology frequently trickles down into other fields, improving everything from medical imaging devices to satellite communication systems, while you won't find a product labeled "now with cosmic void technology." On a store shelf, the influence of this research is woven into the fabric of modern innovation. It pushes the very limits of what is technologically possible, demanding bigger data handling, more powerful computation, and more precise instrumentation. And beyond the tangible gadgets and algorithms, this research provides something perhaps even more valuable: inspiration. The stunning maps of the cosmic web and the profound mystery of these vast emptinesses capture the public imagination, sparking interest in science, technology, engineering, and math among students around the world. They remind us that the drive to explore even something as seemingly abstract as nothingness is a fundamental part of what propels humanity forward, leading to discoveries and inventions that ultimately benefit everyone. But as we chart these territories of nothingness with ever more powerful tools, we are inevitably drawn into a deeper conversation that transcends pure science, a conversation about our responsibilities. The pursuit of knowledge about cosmic voids, while seemingly abstract, is not free from ethical considerations. It demands a significant investment of our collective resources, billions of dollars for cutting-edge telescopes, supercomputing time that consumes vast amounts of energy, and the brilliant focus of thousands of researchers. In a world grappling with immediate, earthly crises like climate change, poverty, and disease, it is a valid and necessary question to ask: why should we devote so much to studying emptiness so far away? This isn't a question meant to halt exploration, but to ensure it is undertaken with mindfulness and a clear sense of purpose. The justification lies in the profound, long-term return on investment. The technological spin-offs from this research, as we've seen, often find critical applications in medicine, computing, and energy. More fundamentally, understanding the cosmos is part of understanding our own origin and ultimate fate. It is a foundational human endeavor that expands our perspective, inspires new generations of scientists and engineers, and provides a unifying, peaceful goal for our species. The ethical approach is not to abandon the quest, but to pursue it efficiently, collaboratively, and with a constant eye toward how its benefits can be shared across all of society, not just a privileged few. This leads to a second, more philosophical ethical layer. As we map these vast, uninhabited deserts of space, we are forced to confront humanity's place in a universe that is overwhelmingly empty and, as far as we know, devoid of any other consciousness. This cosmic perspective can be a powerful antidote to anthropocentrism, the belief that humans are the central fact of the universe. Realizing that we exist on a tiny, fragile oasis in a cosmic sea of nothingness can foster a profound sense of planetary stewardship. It highlights the incredible rarity and value of our living world and underscores our ethical responsibility to protect it. This view of Earth, isolated and precious against the void, was famously ignited by the Apollo program's photographs of our blue marble from space, and void research deepens that perspective exponentially. It argues that our first and greatest ethical duty is to safeguard the one place we know for certain that life exists. Conversely, this same perspective also fuels the ethical debate surrounding future space colonization. The discovery of these vast, resource-rich empty regions could one day be seen as an invitation for expansion, a solution to earthly overpopulation and resource depletion. But this raises critical questions. Do we have the right to claim and potentially alter these pristine cosmic environments, even if they are devoid of life? What principles should guide us? The current framework for space law, based largely on treaties that prevent national appropriation of celestial bodies, is ill-equipped to handle the scale of void exploration. An ethical approach would likely advocate for a principle of cosmic preservation, treating these voids not as real estate to be developed, but as unique natural laboratories and monuments of cosmic evolution to be studied with minimal disruption. It would prioritize the prevention of contamination and the peaceful, international use of any resources we might one day learn to access, ensuring that humanity's expansion into space, if it ever happens, is conducted with wisdom and foresight, not as a reckless scramble. Ultimately, the core ethical imperative is one of open access and shared benefit. The data gathered by telescopes like Hubble, Webb, and Euclid is not owned by any single nation or corporation. It is a heritage for all humankind. Maintaining this principle of open science is paramount. It allows researchers from all over the world, regardless of their funding, to contribute to and learn from this grand project. It ensures that the knowledge gleaned from staring into the void knowledge about our fundamental physics, our cosmic history, and our place in the universe enriches everyone. This balances our innate curiosity with a deep-seated responsibility, ensuring that as we reach out to comprehend the cosmos, we do so in a way that reflects the best of humanity, collaboratively, thoughtfully, and with a reverence for the profound mysteries we are only beginning to unravel. But the future of void research is far more than just a laundry list of new telescopes and simulations. It represents a fundamental shift in how we probe the very foundations of physics. We are moving from simply cataloging these empty regions to using them as precision instruments, and the next generation of observatories is being designed with this exact purpose in mind. The Nancy Grace Roman Space Telescope, set to launch later this decade, is a perfect example. Unlike its predecessors that mapped the cosmos in patches, Roman is designed for a wide-field, high-resolution survey of unprecedented speed and depth. It will essentially create an ultra-high-definition, three-dimensional movie of the universe's large-scale structure, allowing us to track the evolution of thousands of individual voids across billions of years. We'll be able to watch them grow, merge, and interact with a clarity we've never had before, measuring their expansion rates and shapes with such precision that we can place incredibly tight constraints on the nature of dark energy. Is its strength constant, as a cosmological constant would suggest, or does it vary over time? The subtle differences in how voids evolve will hold the answer. This leap in observational power must be matched by a parallel revolution in our theoretical models. For decades, the most sophisticated simulations of the cosmos have treated dark matter as the sole architect of structure with normal matter, the baryons that make up stars, planets, and us as a passive passenger. But we know that's not the full story. Baryonic physics is messy and powerful. Supernova explosions can blow gas out of galaxies, and the intense radiation from quasars can heat intergalactic material, preventing it from collapsing to form new stars. These processes undoubtedly affect the delicate ecosystems within and around voids. The next generation of simulations, with names like Millennium Tingy and CAMELS, are now integrating these complex baryonic effects. By running these incredibly detailed virtual universes and comparing them to the stunning new data from Roman and other telescopes, we will finally be able to untangle the separate influences of dark matter, dark energy, and baryonic feedback on the formation and evolution of emptiness itself. This will transform voids from fuzzy, underdense blobs in our maps into calibrated tools for fundamental discovery. Two of the most tantalizing goals on the horizon involve looking both incredibly far back and deeply into the laws of physics. First, by pushing our observations to higher and higher redshifts, we aim to find the primordial voids of the infant universe. These would be the direct descendants of the very first underdensities that formed from quantum fluctuations during inflation. Studying their initial sizes and distribution would give us a direct test of inflationary theory, potentially allowing us to distinguish between different models of how the universe began. It's like finding the first brushstrokes on the cosmic canvas. Second, voids are becoming the ultimate testing ground for alternative theories of gravity. In the extremely low-density environments within a void, where the gravitational field is weakest, any deviation from Einstein's general relativity should be most apparent. Missions like the European Space Agency's Euclid telescope are specifically designed to measure the subtle distortions in the shapes of galaxies around voids caused by gravitational lensing. If the observed distortion doesn't match the prediction of general relativity, it could be the first evidence that we need to modify our understanding of gravity itself on the largest scales, a discovery that would shake physics to its core. This pursuit is inherently interdisciplinary. The questions we are asking about voids no longer belong solely to astronomers. Particle physicists are deeply involved, as the properties of dark matter particles, whether they are cold, warm, or have some ability to interact with themselves, would leave a distinct signature on the web-like structure of dark matter within a void. Philosophers are joining the conversation, helping us grapple with the profound implications of a universe that is mostly nothing, and what that means for concepts of existence and reality. This collaborative spirit is essential because, as astronomer Sandra Faber rightly predicted, these emptinesses will indeed be at the forefront of cosmology. The path forward is clear. We will use these vast cosmic nothings to answer our biggest questions, and in doing so, we are guaranteed to uncover new mysteries we cannot yet even imagine, ensuring that the exploration of the void remains one of the most vibrant and exciting adventures in science. We have journeyed through the enigmatic world of cosmic voids, from their quantum origins in the first moments of the Big Bang to their role as cosmic accelerators revealing the push of dark energy. We've seen that these vast expanses are not mere absences but dynamic, evolving structures that actively shape the cosmic web, influence the birth of galaxies, and serve as pristine laboratories for testing the very laws of physics. They are the dominant architectural feature of our universe, the great empty rooms that give the cosmic web its form. As the esteemed astronomer Neil deGrasse Tyson once reflected, the universe is under no obligation to make sense to you, and indeed, the existence and behavior of these voids challenge our deepest intuitions about emptiness and reality. They compel us to look beyond the bright points of light and to find profound meaning in the darkness between them. This exploration invites a profound shift in perspective. It asks us to reconsider the very nature of nothingness, to see that what appears to be a void is in fact a complex, structured space teeming with dark matter, traced with primordial gas and dotted with unique, isolated galaxies. It expands our understanding of the cosmos from a story of bright objects to a grand narrative that includes the spaces in between, a narrative where emptiness is an active and powerful force. The next time you gaze up at the night sky, you might not just see the stars, but also sense the immense, invisible architecture of voids stretching between them, a silent, expanding framework that holds the key to the universe's past and its ultimate fate. If this journey into the darkness has expanded your view of the cosmos, if you've enjoyed uncovering the secret lives of these intergalactic voids, then please show your support by liking this video and subscribing to the channel for more deep dives into the universe's greatest mysteries. We'd love to continue this conversation with you, so share your own thoughts, questions, and reflections in the comments below. What aspect of cosmic voids did you find most surprising or profound? Thank you for your curiosity and for joining us on this extraordinary cosmic adventure. Until next time, keep looking up and wondering about the incredible universe we